Okay, good morning. Chapter 5, AC analysis. It's one of my favorite topics, not least because of the math that's involved. Um, let's actually get right away to our slides. And Chapter 5, sinusoidal analysis. The reason we call this sinusoidal analysis is because we deal with sine waves. And so let me explain what you're going to do in this chapter. You're going to learn how do AC circuits work. It's not going to be much different than what we learned in chapters 1 and 2, resistive circuit analysis. We have looked at 3 components in this class. Those are the only 3 components we look at, which is resistors, inductors, and capacitors, right? Resistors, inductors, and capacitors. So they all work nearly the same. Resistors work exactly the same as they did for DC analysis, right? Inductors and capacitors, we'd expect the response to be the same, but there's a slight difference. Okay. When I say slight difference, actually, that's a big difference. The reason is because inductors and capacitors are energy storage devices, right? So they receive the energy and they release it back into the circuit. Whereas resistors receive the energy and then release it as heat. So whether it's a DC or AC voltage or current, a resistor will dissipate the energy as heat. Inductors and capacitors, not much. Okay, they will store the energy and then release it back into the circuit. And so resistors are the same for DC and AC. LNC, different because of energy storage. Okay. And what we're going to learn is how we can mathematically model the relationship for the voltage and current and power for an inductor and capacitor when it deals with an AC voltage or AC current. Okay.
Professor?
Yes.
Have you posted these slides to the OneNote?
Yeah.
I cannot see them for some reason.
Yeah, it's probably not refreshed or something, but we are in OneNote.
Okay, cool. Thank you.
Yeah. All right, so let's take a look at some AC waveforms. Right on top is the most common one. And that waveform is known as a sinusoidal waveform. Okay, hence the title of this chapter, sinusoidal analysis. This chapter can be called AC analysis, right? AC analysis. The reason I have listed it there is because the book that I use has the same title. Mathematically, this waveform can be represented with either a sine or cosine function. And that's where the name comes from, sinusoidal, because it's sinusoidal in nature. So mathematically, we deal with the sine and cosine functions. As you can see here, and we'll look at each of these components individually in the next few slides, but you can see here, the waveform varies from a positive value to a negative value constantly. It goes up, it goes down, it goes up, it goes down, goes up, goes down. Okay. The value of that waveform on the y-axis changes. It's different at any given point in time. On the x-axis, we have time. Here it's referenced as milliseconds, but it could be seconds, it could be minutes, it could be anything. But at any given point in time, the value of that function, the value of that voltage or current or power is different. It's not the same. Okay. It alternates between a positive and a negative value. And hence, we call it alternating current. So when they first came up, when researchers first discovered electricity, or a way to actually generate electricity, it was from a circular generator, and hence alternating waveform. So alternating current. That's where the name AC comes from. So if you think back to the first day of class where I talked about the difference between DC and AC, and I referenced DC stands for, anyone remember? Direct current. And AC stands for alternating current because it alternates between a positive and negative peak. Okay. The reason is a generator rotates between magnetic poles. So when it rotates between magnetic poles, it goes to the North Pole, South Pole, North Pole, South Pole of that magnetic field. And the current that's generated goes positive, negative, positive, negative. There are some cool YouTube videos available on the web. I'll try and bring it up next class. Then there are triangular waves, square waves, ramp, rectangular, or pulse. All of these are just different kinds of waveforms. For the most part, the entire chapter for AC analysis for this entire course, actually, not just this chapter, will deal with sinusoidal waveforms. That's the only one that we're going to look at. There's mathematical theory that you can take any waveform, any periodic waveform, any repeating waveform, and you can represent it as a sinusoidal function. So they're all sinusoidal in nature. So let's look at the mathematical representation of a sine wave. Okay. Voltage, it could be V or I or P as a function of time. Remember, we are describing the quantity which has different values at any given point in time. So mathematical representation of this quantity or this function is time dependent. So this expression applies equally to V of t or I of t or P of t. There are three quantities in there. Subscript m, omega, and theta. That m stands for magnitude. It describes the value of that quantity on the y-axis. Okay, it describes the value of that quantity on the y-axis. X-axis is always time. Okay, y-axis is, of course, your function, which is either voltage or current or power. So the first quantity in there, which says Vm, Vm describes the y-axis value of that waveform. It is also referred to as amplitude or the peak value. Okay, so this specific term right there, this specific value, Vm, is also written as Vp. If you have taken the lab and you use the oscilloscope in lab 5, you would have come across the term Vp. It's the same as Vm. Okay, Vp and Vm are the same. And it describes the value of one peak, not peak to peak. So it describes the value of one peak. If you wish to calculate the value of that waveform from both peaks, you'd multiply it by 2. And that would be referred to as Vp-P. V peak to peak. So from the positive peak to the negative peak. Okay. Now it could not always be positive or negative, depending on DC component. I'll talk about that in a couple of slides. So the first value of that waveform, Vm, describes one peak, the peak value of that waveform. Then we typically represent the waveform using the cosine function. Okay, so cos omega t plus theta. Omega is the angular velocity or the angular frequency in radians per second. And it can be broken down into 2 pi f. 2 pi f. And we'll look at the graphical illustration in just the next slide, where it will make a little bit more sense. Okay, omega is 2 pi f. Theta is the phase angle in degrees. F is the frequency of the waveform. And with regards to time, it is the inverse of time. So F is 1 over t. Okay, F is 1 over t. T is uppercase. That's the time period of the waveform. But again, this is the most important representation of the AC waveform, a sinusoidal AC waveform. And you will use this over and over again till the end of this course. Okay. Okay, so three quantities. I said we look at the amplitude or the magnitude, the frequency, and then the phase, right? So amplitude, as I said, describes the value of the waveform on the y-axis. So it tells you how tall or short the waveform is. So basically, it is giving you this value. On the y-axis measured from y equals 0. Okay, so Vp or Vm is the value on the y-axis. In these examples, you can see the first value, 0.5, 1, and 2, right? The shortest one is the waveform in red, has a value of 0.5, 0.5. The second waveform, it's not listed. If it's not listed, it's 1. So it's 1 sine theta. And then, of course, the third one is 2. So if you equate this equation with Vm cos, this could be either sine or cos. You take the first value in there, that's the peak value, that tells you the value of the voltage or the value of that current. Make sense? Then we come to frequency. Now, I said that the value of this waveform goes up and goes down, goes up, goes down, bounces between a positive and negative value, right? It goes to a positive number, then comes down to 0, then goes to negative number, comes back up to 0. So when a waveform starts at 0, goes to a positive peak, comes back to 0, goes to a negative peak, and then returns back to its original starting point or original starting value, that is known as one full cycle. Okay, this is known as one full cycle. One full cycle. And the number of times it bounces between positive and negative in 1 second is known as the frequency of that waveform. So how frequently it repeats that cycle in 1 second. Number of cycles in 1 second gives you the frequency. It is noted by the lowercase f. It's the number of cycles in 1 second. Do they cover this in physics? Okay, then I'll go faster. Frequency is obtained from omega, from that waveform. And so this is 2 hertz, 1 hertz, and then half a hertz. Unit is named after the German physicist Hertz. Can't recall his first name right now. The unit is Hz. Okay. And then finally we come to phase. How many of you will be able to describe phase? Kind of, not so much. Phase is basically the point in time where the waveform crosses the x-axis. Okay, the point in time where the waveform crosses the x-axis. So if you look at the second waveform, the one shown in black, you can see it crosses the x-axis exactly at y equals 0. Sorry, x equals 0. Right? It crosses it right there at x equals 0. So the phase or the phase angle of that waveform is 0 degrees. Okay, so it's 0 degrees. 0 degrees. On the x-axis, we have time, right? Time. If you look at the blue waveform, the waveform in blue, so this is the future. This is the past. If you look at the blue waveform, with relation or with respect to the black waveform, the blue waveform has arrived earlier or ahead of the other two. Think on that statement for a few seconds. The blue waveform is ahead in time of the other two waveforms. X-axis, positive value is the future. If we are analyzing a circuit here where time t equals 0, then anything to the right is in the future, anything in the left is in the past. So when waveform, the second waveform, arrives at x equals 0, the blue waveform has already gone past. And so we say that the waveform in blue is ahead with respect to the other two waveforms. Technical term that we would use is leading. Similarly, the waveform in red is behind. Technical term we use is lagging. This is going to be important because in a capacitor and an inductor, the voltage and current are not in phase. Okay. For an inductor, the voltage leads. For a capacitor, the current leads. So there's a phase difference of 90 degrees for them. And so understanding phase is very, well, I would say it is important. All right, any questions about phase? Well, phase, frequency, or amplitude. Okay. So when they first came up with AC waveforms and they were trying to describe the transmission of power and energy, they ran into a problem trying to describe the value of this waveform. What is the average value of an AC waveform? If half of it is above and half of it is below 0, what is the average value? 0, right? Yet energy is being delivered, right? From an AC generator, energy is being supplied, it is being received by the circuit. So mathematically, they needed to find a way to describe this value. So what they did was, instead of taking the average of the waveform itself, they decided we would square the waveform. Then we would take the average of the square. And then because we took the square before, now we'll take the square root at the end. And so they came up with a value known as the root mean square. It literally is the root of the mean of the square of the value of the waveform. Hence, root mean square. Mean, of course, is another word, is a synonym for average, right? So it kind of describes the average value of that AC waveform. If you take that mathematical function, you would square it, which is right here, v square. Then you'd average it out. Averaging is basically integrating for one time period, meaning from 0 to t. Then average it out, meaning divided by t. And then you take the square root, hence the root of the mean of the square. So you square the waveform first. You find the mean. Is basically integrating means adding all of the slices, divide by t, which is the number time period, and take the square root. So the subscript RMS stands for root mean square. You can have VRMS, IRMS, even for power, right? Any time varying signal, you can find the RMS value. So P average, the equation comes from P square, P is V square over R, or I square times R. That's where it comes from. So for an AC waveform, if you wish to find average power, then average power for an AC waveform is simply the square of the RMS voltage divided by the resistance and square of the RMS current times the resistance. For sinusoids only, for sinusoidal waveforms, when you calculate, when you take a sine wave or a cosine waveform and you do the mathematical calculation, it turns out that the relationship between the RMS value of the waveform and the peak or the magnitude of the waveform is given by these equations. And so I can write VRMS is Vm divided by root 2. IRMS is Im divided by root 2. If you are given a peak-to-peak value, you would divide by 2 first to find one single peak value and then calculate RMS from there. Okay. All right, any questions? Any questions at all? All right, we'll end class here today, and we'll pick up here again on Wednesday. Open up the homework for sinusoidal AC analysis. I think right now it's due for Wednesday or Thursday, but these concepts should be enough to get you started on the short answer questions. Okay.